I'm David Leavitt. I am a graduate student. Hopefully, someday I'll complete my work at Oklahoma State University. And I also am an employee and principal of a company called the Hecto Group, which is located in Olathe, Kansas, and in St. Louis, Missouri. So I'm going to talk about a technology that we think is really promising for cleaning up produced water and making it fit for recovery of valuable elements such as lithium and bromine and iodide. And this technology is called membrane distillation and crystallization. I'll just say a few words about collaboration. This is very much a collaborative effort between Oklahoma State University, Colorado School of Mines, and the company that funded the research, the Hecto Group. So I've noted them and acknowledged them on this slide here. One of the Hecto Group subsidiaries is called Solute Smart, and Solute Smart is devoted to looking to new and novel technologies that can clean up water. So that's kind of an introduction to the work. Okay, so we all know that the Mid-Continent area has a produced water problem. That's the focus of this hearing. I have a slide here that just talks about how much water is being produced in oil and gas productions, 1.5 million gallons to 16 million per frac job. And I note that about 21 million barrels of produced water are generated in the US every year. So this is a lot of water. It is always difficult to process because produced water contains many of the minerals that are found in connate water that comes up when oil and gas is produced, plus some of the chemicals that are injected into a well to fracture the formation. So it's a real mixed bag. And of course, here in Oklahoma and the Mid-Continent, we know that underground injection produced water, which is the most common way of disposing of it, is known to induce earthquakes. So it's a problem to be resolved, but it's our contention that it's also a resource that we can tap into to mine the valuable elements in them if you have a good technology that's cost effective for doing so. So some of the process for produced water resource and treatment have to do with evaporation and with membrane distillation. The key is that the volume of produced water, even though oil and gas will eventually have a downturn, the volume of produced water and also the volume of highly concentrated brines, not just from oil and gas production, but from wastewater treatment and from other sources, is going to go up in the future. And a way has to be developed to effectively remediate it. A lot of the current processes for treating produced water are related to membrane technologies to separate out the dissolved solids from the pure water. Membrane technologies are great, such as RO, but many of the high pressure membrane technologies are not really effective when the concentration of dissolved solids in the water that you have to treat gets above 40,000 milligrams per liter or so. Tend to have a lot of fouling occurring then in the membrane, in some cases damaging in the membrane, and reduce efficiency for removing the water. So we're looking at technologies that focus on low pressure membrane separation of the constituents in water from the pure water, such as forward osmosis and membrane distillation. And here we're going to talk about some work we did focusing on membrane distillation. So that's kind of the focus of the work that we've done collaboratively. Now, I just put this slide up here to show that Oklahoma produced water is really a resource. These are some data taken from the USGS survey for strategic materials that was done several decades back that looked at many of the formations across the Mid-Continent, including formations in Oklahoma, and analyzed them for their constituents. And if you look here at the first line item on this chart from the Gibson Formation in Oklahoma, you can see that this formation contains 1,730 milligrams per liter lithium. That's a lot of lithium. So most brines that are used, non-oil and gas brines, but other concentrated brines that are used for capturing lithium contain 100 milligrams per liter. So there's an opportunity here if you can treat this material to mine it for lithium that can be used for batteries and other downstream applications. And also the gypsum has a healthy amount of bromine and iodide, as you can see from that chart. If I move my cursor, does that show up so that you can see it?
Yes.
Okay, good. So I just wanted to point out the amount of lithium that's found in some of the formations in Oklahoma. And in the trade literature, it's disclosed that if you have a brine that contains 50 milligrams per liter lithium or more, there are technologies that can be used now to take that brine and in a cost-effective manner extract the lithium from it. So you can see we have a lot of formations in Oklahoma that are already past that threshold for mining, including Mississippi Chat and the Arbuckle, and many formations that I haven't listed here that could be concentrated up to make a resource material that could be processed for lithium and iodine and bromine if you have an effective way of doing it. So that's the purpose of this slide, show that Oklahoma produced water is a resource. We just need to utilize it as a resource instead of a waste problem. So we took a look at how we might do this in our collaborative group, and we focused on membrane distillation. Now, membrane distillation is pretty low cost and it's pretty selective for producing produced water. It can be used to recover valuable minerals. It's been done to do that before. There's a number of studies in literature about that. Also studies done showing it's cost effective in limited applications. It's not a technology that you hear about commercially. It's relatively new. It doesn't nearly have the track record in commercial use as the high pressure membrane separation technologies such as reverse osmosis and ultrafiltration and nanofiltration. But more and more it's becoming an area of investigation and promise. There are also studies showing that membrane distillation with crystallization can form a suitable process for capturing lithium from concentrated brines. So that's why we picked it. We looked at it as an area that we might investigate and find promising. So just a little slide about what it is. It's a low pressure process that permeates water vapor across the membrane, not liquid water. So it permeates water vapor across a hydrophobic membrane, leaving the salts on the feed side of the membrane and releasing water vapor on the permeate side of the membrane that can then be condensed or captured in a highly purified form. It's also good for treating endothermic salt solutions and other materials, not just produced water. Unlike pressurized separation techniques such as reverse osmosis and ultrafiltration, the driving force for permeation isn't pressure, but it's the temperature difference between the feed and the distillate. So the temperature difference is the driving force. So you have to have the feed at a higher temperature than the permeate or the distillate side to drive the mechanism forward. It works by creating a vapor pressure gradient across the hydrophobic membrane. So when that happens, the brines are concentrated. The salts in the feed that are there, the dissolved salts in the feed, start to crystallize, and then they nucleate out. So there's a really sweet spot with using membrane distillation on how you want to operate it. You can operate it to take a brine all the way down to a crystallized slurry, if that's your intent, or you can remove less water and create a flowable material that can be processed downstream. Characteristic of membrane distillation is the flux increases with an increase in temperature difference. It's in the work we found, and I'll get into that in a minute, a really good parameter is to keep the delta T between the feed and the distillate of around 30 degrees C. If you have around 30 degrees C, you get fairly reasonable flux. One other point to know is that membrane distillation is independent of the concentration of the feed. And this is a really good point because with reverse osmosis, as I mentioned, when some of the other high highly pressurized separation technologies, if you get above 40 to 50,000 milligrams per liter, which a lot of oil field brines are way above that, then it's not very effective. But with membrane distillation, the concentration of the feed doesn't have a significant effect until you finally start crystallizing material out of the feed solution as you remove the water. So RO typically processes brines less than 60,000 milligram per liter total dissolved solids, and literature and also our work is shows that we can process up to 600,000 milligrams per liter total dissolved solids using membrane distillation. And then here's some another slide here that I won't go into because I have a lot of slides, just showing that membrane distillation can be followed up with membrane crystallization to capture the crystallized nucleated salt materials on the feed side of the membrane and remove them. A point to note about that, especially in light of Mark's discussion, is that the modeling of how the salts crystallize is really important in the operation of membrane distillation. We tend to use in our work a product called the OLI Studio Stream Analyzer, which is a software model that's used in the oil industry to predict corrosion and scaling of different mineral species that might be found in oil and gas produced water over time as the produced water increases in concentration. So as you can imagine, you have a real mixed bag of many different type of elements in produced water. They all have their own unique chemistry. As the temperature of the feed increases and the concentration of the feed increases, then the solubility of the various minerals come into play and they tend to fall out. And it's good to be able to predict that so you can know how to operate your unit. Okay, so why do we want to use it? We feel it's an effective, low-cost way of extracting pure water from the brines. And it can also be used not on just oil and gas production, but we've shown that it can be used with our collaborative group to treat endothermic salts as a refrigerate and cooling agent. And these endothermic salts typically have total dissolved solids of 500 to 600,000 milligrams per liter, and membrane distillation works really fine for that. And we believe that it's a good operation for recovery of lithium, bromine, and iodide, and rare earth too, although we haven't treated any brines yet that have rare earth in them. Okay, so I have a little slide here that shows more attributes of membrane distillation. It's a process that can be driven by low-grade waste heat, and there's a lot of waste heat that essentially isn't utilized, that could be utilized in a technology like this. Evaporation temperatures for effective evaporation and pressurized evaporation systems typically operate at 80 to 90 degrees C. Membrane distillation can operate at 60 to 50 degrees C, as long as you have appropriate delta T between the feed side temperature and the distillate side temperature. So one note I want to make is that when you use waste heat, you essentially can replace electrically driven processes such as reverse osmosis, where electricity is used to drive a compressor, with thermally driven processes. And that gives you potential for a really effective cost savings. Okay, so that's just another slide to talk about that. Now, I won't go into this whole lot because I'm afraid I've prepared too many slides like I usually do. Anyway, this is a schematic showing the different types of membrane distillation that can occur. The first type in A is called direct contact membrane distillation. There you have the feed going across the feed side of the membrane in a loop, feed loop, where the raw feed comes in and the concentrated feed comes out as the water is removed across the membrane. Unique attribute of direct contact membrane distillation is that the membrane that is directly exposed to the feed material, and on the opposite side of the membrane, where the distillate is, where the permeate comes out, the membrane is in direct contact with the permeate as well. So you have two loops. One is a feed loop that recirculates across the membrane, and the other is a distillate or permeate loop that recirculates across the membrane. And the driving force is temperature. But there are a lot of other ways you can make it work. You can insert a gap between on the permeate side of the membrane, so you don't have direct contact with the liquid, but as the membrane, as the water vapor permeates through, can hit a condenser and then condense on the liquid as a liquid on the condenser and then flow out. That would be called air gap membrane distillation. You can also apply vacuum on the permeate side for vacuum membrane distillation to improve the flux across the membrane, and a number of other configurations. But what we chose is direct contact membrane distillation because it's really simple to do. It has two separate loops, a feed loop that recirculates across the feed side of the membrane and a permeate or distillate loop that recirculates across the permeate side of the membrane. It's simple to use, simple in concept, and require a lot of expertise to operate and control it. And it doesn't require a condenser for distilling vapor like in air gap membrane distillation. So we use that in the work that we did in our laboratories. Okay, so here's a typical lab setup that we had at OSU. Down here it has a heater chiller for the feed side, another heater chiller for the permeate side, the distillate tank that serves the distillate loop, the feed tank that serves the feed loop. And although we have a really high pressure pump on here, we really didn't need it. We could have used a low pressure pump. So we scaled that back during our operation. And this is a small low pressure pump for the distillate recirculation. So that's kind of what we used at OSU. And we used it for a while. It was pretty hard to use because it wasn't automated. A lot of the studies we have go 20 or 30 or more hours. So eventually we moved that into Hecto Group's laboratory when they took their laboratory space at the Kansas Bioscience Park in Olathe, Kansas, and continued our work there. And finally did the substantial amount of work with our collaborative partners up at Colorado School of Mines. So the nice thing about the Colorado School of Mines setup is that it's fully automated. It can run a variety of different configurations, direct contact membrane distillation or air gap membrane distillation. Everything's all put in place. You can see this is the unit that we used. This device on top is a spiral round tetrafluoropolyethylene membrane that we've found to be very effective as the membrane module. And we have the various other equipment that's there. It's described. Here's a little bit more detail about the membrane that we use. You know, the membrane is a key. There are a lot of different membranes that are hydrophobic that can be used for membrane distillation, but not all of them have good shelf life. Many of them, when the scale forms on the feed side surface, the scale is very difficult to remove. So we lucked out. I guess I won't call it luck. It was really the expertise of the folks at Colorado School of Mines on testing many, many different types of membranes that came up with this particular tetrafluoropolyethylene membrane called the Clarcor QL822. And this membrane wasn't even designed for membrane distillation. It was actually a membrane designed to remove soot from diesel exhaust engines. But it worked really well in the work that we did, and we went forward with most of the work on it. So as I said, characteristics of the membrane is really important. Membrane in membrane distillation has to be hydrophobic. It has to have good porosity, low thermal conductivity. That's the key thing because you do get heat leaking from the feed side into the permeate side. And as heat leaks into the permeate side across the membrane, then the delta T between the membrane decreases and your driving force diminishes and your flux goes down. So you have to have a way of not releasing too much heat across the system. So low thermal conductivity is important. And the membrane has to be chemically resistant and thermally stable. So when we focused on the tetrafluoropolyethylene membranes, that's essentially a Teflon type of membrane. It's very inert to a lot of the chemicals that are found in produced water. It has good shelf life, it doesn't deteriorate, and the surface roughness characteristics of the membrane are such that when crystals form on them, most types of crystals that we found form on top of the membrane are easily washed off, so the membrane can be recovered. Some of the factors that affect membrane distillation are fouling. That also affects high pressure separation technologies. Fouling is where organic material or other material clogs the membrane pores, forms a layer on the surface that reduces the ability of the membrane to permeate the water through it, clogs the pores up. Scaling is another factor. That's why I mentioned using the OLI software corrosion packages that predict thermodynamic and kinetic that use thermodynamic and kinetic data to predict the scaling of different materials and different minerals on top of a surface as the feed water is concentrated. Calcium carbonate salts can also penetrate into the pores. So if you have a really high dolomitic type formation, you can have trouble with them. So scaling is something you have to look at. Some of the challenges are selecting that appropriate membrane, controlling the polarization that occurs across the membrane itself that reduces flux, and reducing wetting and fouling. A phenomenon of membrane distillation is that as the cake or crystalline material builds up on the feed side, it can cause a phenomena where water vapor doesn't penetrate the membrane in the vapor phase, but it actually penetrates as liquid water. If liquid water goes through the membrane, it will take the dissolved solids with it, and you get what's called a wetting of the membrane and reduce separation. So we have to control that too. Okay, so
I want to do a quick time check. We got about 5 more minutes. So.
Oh my goodness, I've talked too much. Well, let me go through this real quick. I'm sorry. So we looked at, I'll just cut to the chase. We did a lot of work. We went around and we took samples from First Wilcox, Woodford, Mississippi, Hunton brines from Oklahoma, Thornton brine from Colorado, Permian brines from Texas, gathered them up. Here's a picture of the different samples we have going from, on this side, the raw water to the Permian and here that we process through our material. Here's an analysis you can look at later. A summary of the analysis showed that we tested waters that had a conductivity ranging from 250,000 to 60,000. The waters also contained lithium from 8.88 milligrams per liter lithium in the Thornton to 2.1 in the Hunton Formation in Oklahoma. And as I'm sure everyone knows, a lot of produced water contains radionuclides. So naturally occurring radioactive material is present in these brines, and we found it in the form of radium-226, 228, and thorium. So let me just jump down here. This just shows you a graph of how we start out our work by running the OLI scaling prediction. This was on the First Wilcox water. It shows us where the different scaling minerals will come out and allows us to determine, based on water recovery, what kind of a scale material we should anticipate so we can operate the unit accordingly. On the First Wilcox water, this showed calculated water flux after 20 hours. Our water flux was really high, 25 liters per meter square per hour initially, but as scale and crystals build up, the flux went down as the driving force went down as well. Okay, conductivity on this particular, I'll just show you this, a few of these slides with First Wilcox. Conductivity goes up and not too bad. It's still much lower in the distillate than it is in the produced water. So we essentially are producing essentially pure water, RO quality water, using membrane distillation from oil field brines. Our volume of water goes up over time, as you'd expect in the distillate. Water recovery, typically 60 to 70%, depending on how concentrated the brine is. Sometimes we can get as high as 85% recovery of water from oil-filled brines. These are just some slides showing our concentration factors, salt rejection. This is a quality control slide showing the temperatures that we're operating under in the feed and the distillate. I'm going kind of fast with these, and I apologize for that. We also calculated thermal efficiency of the membrane and looked at heat transfer, conductive and convective heat transfer, and measured it across time. So the typical type of membrane cell module showing it disassembled and some of the crystals that are forming on the feed side. And this is some of the concentrated produced water from the first Wilcox formation in Oklahoma that we chilled and dropped all of the salts out, showing that we can process these salts further to recover the minerals that are in them. Okay, this is just a slide, another picture showing how scaling can form. This is before and after operation of flat plate flow cell membrane. Okay, we also did comparative trials. We looked at the Teflon membrane, PTFE membrane versus polypropylene membrane, and looked at their flux and water recovery, and I'll just jump to the chase on that study. Basically, when we looked at the distillate conductivity for the polypropylene membrane, it reached a certain point and we had breakthrough. The membrane was fully wetted and no longer permeated water vapor, where when we looked at the Teflon membrane, which I don't have a slide on, it was very constant and very good for at least 4 or 5 intervals of time longer. Instead of breaking through at 15 hours, it started to see an increase in the conductivity of the distillate after 120 hours. This just shows some of the crystals that form on the membrane that we have to identify and predict in terms of our ability to remove them. That it? I still have about 2 minutes.
You can give your final summary if you want to real quick, but yeah, we're about out of time.
All right, this is just a slide showing the difference between the two membranes and how the Teflon membrane outperformed the polypropylene membrane. So here are some conclusions. With our first Wilcox, we got around 60% water recovery, an average flux of 8 liters per meter square per hour. The total dissolved solids of the distillate was less than 200 milligrams per liter. Of the untreated produced water started out at 146,000 milligrams per liter. So that was pretty good recovery of pure water from the brine. Mississippi was similar, 60% water recovery, ending up with a distillate containing 120 milligram per liter. Total dissolved solids starting out with the produced water at 154,000. Woodford, 70% water recovery. Similar story, Hunt and Brine, 86% water recovery. So we had good results in recovering pure water. We also found that in the study we did on the Thornton produced water, we increased the concentration of lithium from about 8.8 milligram per liter to 52.5, which is above that threshold point that literature says that water containing that much lithium is good as a ore body for processing. And in that case, the distillate still contained less than 200 milligrams per liter total dissolved solids. Interesting point was that we also concentrated up the radionuclides. So in the Thornton study, we started out with 9.25 picocuries per liter of radium-228 and 62.3 picocuries per liter of radium-226. The concentrate that retained after many days of operation contained 866 picocuries of radium. So we're getting a lot of radium, but it's not going in the permeate. We did have a study that was really an anomaly, and we're trying to investigate now, where we found that the radium went into the permeate and not in the concentrate. I think that's probably due to the membrane being wetting. Okay, so that's all I have. Yeah.
Thank you very much, David. Sorry, guys, we're running over on time. We did have one question for you, David, and it was, what is the upper TDS of untreated water that can be treated with membrane distillation and by RO?
Well, we didn't do any comparative studies with RO, but from the literature, it looked to be about 60,000 milligrams per liter of total dissolved solids is an upper range. There are some new technologies out there that might go above that, but that's about as good as we've seen in our literature review. But we have treated with fertilizer solutions, a fertilizer slurry containing 600,000 milligrams per liter total dissolved solids, and effectively dewatered it and captured pure water from it at a good flux rate. The highest produced water that we treated was around 150,000 milligrams per liter.
Gotcha. Well, David, thank you very much. And I want to thank everyone for participating today. As always, it just seems like we don't have enough time, but thanks everyone. Our next one is on July 9th, and we'll have 3 speakers again. We'll have Prem Makina from Oklahoma State, Christine Watson from OSU Tulsa, and Sukjin Kim from OSU talking about some of their treatment technologies. So thanks again, everyone. Hope you all have a great weekend. If you have any further questions, feel free to follow up with the speakers or send them to me, and I'll get them out to them and get you the contact information. But with that, we'll end it for today. Thanks again, everyone.